Thank you, Savandi, and thanks everyone for having me today. You can't see, when I share my screen, you can't see your own faces on it, can you? Yeah. All right, cool. So I feel a bit of a fish out of water in this group. So a lot of the talks are looking at how to use sort of graph packages to solve real world problems. But what I'm interested in is actually improving the algorithms that run these graph packages. So today I'm going to present some work I did last year during a research fellowship at Melbourne Uni with my colleagues, Simon Bolly and Professor Kate Smith-Miles, on how you can sort of learn to combine, using machine learning to combine shortest path algorithms to get a better performing shortest path algorithm. So Kate Smith-Miles is speaking tomorrow on her instance-based analysis framework. At least I'm hoping she's going to cover. So I'm going to handball a bit more of the details over to her tomorrow. So I'll just move. But, essentially, she's done this brilliant methodology, developed this amazing methodology called instance-based analysis, which essentially allows you to empirically visualize algorithm performance. So what this visualization is a whole lot of different instances to a single problem. I just took this because it's the prettiest, but you can think of it as like a network flow problem where each dot corresponds to an actual instance of the problem. Each color corresponds to a different algorithm. And the kind of the space is a two-dimensional projection based on features that you can measure of those instances. So what I'm interested in this talk is whether you can use this methodology to combine algorithms in a clever way, such that you've got a new algorithm that takes the best of both worlds. An example that kind of illustrates this really nicely is sorting algorithms. So Zoom getting in the way. So I'm not sure if you know, but so sorting algorithms, sorting a list. Two of the really most famous sorting algorithms are merge sort, which is recursive, so it has an n log n worst case complexity. So essentially it gets a list and keeps breaking it into smaller groups and then sorting the very small groups and then building it back up again. And then insertion sort, which is non-recursive and has a quadratic worst case complexity. And then someone noticed that if you use merge sort, so in general, you'd think merge sort would be better because of the complexity, but someone noticed that empirically, once the list gets small enough, efficient implementation of insertion sort is actually quicker. So you can actually join these two by using merge sort until the list gets under the size of 10, and then flipping over to insertion sort, and you get a 15% roughly improvement. And that's actually how sort works in Python and Java. This is a simplified version, but the idea is it's used in practice in Python and Java. I'm not sure about R, so I can't comment. But I really like that idea of you have two algorithms, find a clever way to bring them together, and you get a better algorithm at the other side. So I'm interested in doing whether we could do this for shortest path problems. So the shortest path problem, as many of you might know, is finding the shortest path from a source node to all other nodes given an arc labeled graph. So your solution to that would essentially be all the nodes have a distance which corresponds, and you have a tree, which is your solution paths. So to get to C, the shortest path was first going from S to A and then from A to C, and your total distance is 2. So there's been this a stack of algorithms presented for this. The most famous is, and they go back to the 1950s, right? So the most famous is Bellman-Ford-Moore in the 1950s, and then also probably Dijkstra you might have heard of. But there's also a lot of others, and they just have these kind of obscure complexities, and they work in interestingly different ways. I'm not going to go into the details in a 10-minute talk, but essentially there's a lot of different algorithms proposed that work in different ways. So I'm hoping that some have strengths where in certain regions. And so this is something I noticed, that you could sort of break a big graph up into a lot of littler graphs and then use your shortest path algorithm on those little graphs. So how you do that, just in broad strokes, is you can get your your network and then look for strongly connected components. So these are nodes that you can go from any other node, from that node to any other node in the component. So I represent these with the pretty colors. Then once you've got your strongly connected components, you can track the arcs inside each component to get a direct acyclic graph. This is called the condensation of a graph. Once you've got that, you can develop something called the topological ordering. Essentially, that's just an ordering, so numbers to each of the nodes, such that the predecessor of each arc will always be less than the value of the successor. And then you use this ordering to kind of look at, to tell your algorithms what order it should look at the components. So essentially going from left to right, consider this strongly connected component first, find the shortest distances, and then do the next one, the next one. And in doing so, you never have to repeat any of the shortest path calculations. And then in doing that, what we realized is that you can actually use different algorithms for different subcomponents. And so if we can work out features of a subcomponent that lend themselves well to a certain algorithm, then we can use that algorithm for those subcomponents and then stitch it all together. So that's sort of the broad strokes idea of what we're trying to do here. Unfortunately, no dengue fever equivalent, but I still find it interesting. I think it's, yeah. So the graph, so to do so, you essentially need to come up with a way to generate any possible graph. I won't go into the details, but I like these pictures. But essentially, if you give me a density and a ratio of negative arcs to positive arcs, I can generate a graph that hopefully that will be very much close to those values. And then so essentially I generated many instances of these graphs with a good spread of features. So you can see that there's graphs with a lot of many negative arcs, and there's also graphs with many positive arcs, really sparse to really dense graphs, and then graphs with very small minimum absolute value of the weight arcs, and then one very high. And what that gives us is, what Kate's framework does is it allows you to detect regions of the graph where certain algorithms would do well. So just putting this in and getting it straight out is, we find 4 algorithms that sort of dominate different areas. So I won't go into the details of what they are. But the interesting thing is that using just this really support vector machine kind of simplified machine learning algorithm, we can already detect on average across all the instances, just using the predictor, we will perform, the time to solve the shortest path instances will actually be less than any of the individual algorithms, which is great. But in doing so, there's still a fair way off. So 20 milliseconds or what, 30–40% off what is possible. So I consider this work really just a prototype of what's possible of this idea of stitching together different algorithms. I wouldn't say that currently a 2D projection is the way to do it, but it's pretty cool that straight away you're getting results that are already better than what's out there. I'll end by saying that, so I'm not sure if it's been mentioned yet today, but the group at Melbourne Uni have developed this amazing, it's called Matilda, so Melbourne Algorithm Test Instance Library with data analytics, where you can just upload it to CSV files and generate very similar results to that I've presented today. So if you're interested at all, please check that out. Cool, thank you.